Soteria is a fully automatic hip exoskeleton that's designed to prevent falling in the elderly. It does this by tracking away a person moves and then providing corrective forces to their legs in order to ensure that they always stay balanced as they walk. In order to realize this project, we've split it up into 4 main subsystems, namely the sensing subsystem, the processing subsystem, the mechanical subsystem, and finally the actuation subsystem. The sensing subsystem consists of IMUs or inertial measurement units, which we've placed at certain critical points on the frame of the exoskeleton. These sensors help us measure linear accelerations, angular velocities, as well as orientations in space. We've been able to integrate these sensors in order to obtain roll and pitch, which are 2 important angles that we'll be using in our further computations. As you can see from this demonstration, we're able to obtain the roll and pitch corresponding to one leg of this user.
For our swing leg detection algorithm, we used the random forest classifier model to predict whether the leg was in swinger stance. We used IMU values from IMUs placed at the distal femur for this model. The IMU values used were linear acceleration in X, Y, and Z, angular velocity in X, Y, and Z, and roll, pitch, and yaw. We compared this model to ground truth by using FSRs we placed at the bottom of the foot, one at the toe and one at the heel, to give us ground truth whether the foot was in stance or swing. To demonstrate our swing leg classification model, we had a user walk on the treadmill. As you can see, the model predicts whether the user is in stance or swing and plots this on the graph.
To calculate the center of mass velocity, we take the IMU's roll and pitch for the stance leg to get the angular velocity, and we regard the stance leg as an invert pendulum model to change the angular velocity to the linear velocity of the human center of mass. As we can see from the top plot is for the forward velocity, with the mean value close to the treadmill's velocity, and the bottom plot is the lateral velocity, with the mean value close to 0.
Our mechanical subsystem houses all of our components, which consist of 4 actuators, 2 at each joint, our IMU sensors, as well as our onboard computer. So we started off this process by first building a cardboard prototype, which we used to make sure all our dimensions were correct. This is the most recent mechanical design of our system. In this design, we have PVC pipes for our leg linkages and connections, and aluminum plates for our back plate, as well as frames for our actuators. This semester, we built half of the exoskeleton frame, which we then put on a user in order to test for secure and comfortable fit.